Hello everyone, my name is Drew Mills, and this is my lab report on the motion of a falling slinky. My goal was to analyze and predict how a slinky behaves when dropped from rest, specifically the physics behind why the bottom of the slinky appears to stay stationary even after it's released. By comparing an observed model from Tracker with a computational model I built in GlowScript, I discovered that the bottom of the slinky remains stationary until the top part fully collapses into it. Here's how I arrived at that result. To model the system, I identified the slinky as the system and the earth and air as the surroundings. I used three core physics principles, which was Newton's second law. I used the momentum principle to iteratively update the slinky's velocity and position in GlowScript, and I use gravitational force, a constant downward force acting on the mass, and drag and tension. I accounted for air resistance and initial slinky, tension on the slinky. While the slinky is extended, the upward tension force at the bottom exactly balances the downward force of gravity. This is why the bottom doesn't move iteratively. I got data from the video I decided to use using Tracker. I set my initial conditions based on physical properties of the slinky. So the mass is 0.218 kilograms. The initial position is negative 0.0016 and 0.0002 meters. Initial velocity 0, and obviously the gravity constant's 9.8. I used two different while loops to reflect the two phases of the drop. The first one is the collapse. In that first loop, I did it from t equals 0 to 5.53. The slinky is still collapsing. I modeled the net force as the sum of the gravity and tension. Because they are equal and opposite, the net force on the bottom is 0. You can see in my code where I update the position based on this 0 net force. In the second loop from 5.53 seconds to 8.13 seconds, the top has hit the bottom. The tension is now gone. The net force is now gravity plus the downward resisting drag force. Update the velocity and position at each 0.01 second time step to track its acceleration to the floor. When I plotted my predictive model against my observed data, the result was nearly identical. Both show a flat line for the Y position until about 5.5 seconds, followed by a sharp quadratic curve as the slinky falls. So sources of air. One could be external forces. Slight air currents in the video might cause minor fluctuations, seen in the orange dots, and also human air. Manually clicking the center of mass in Tracker can lead to small deviations from perfect blue lines in the model. So what does this mean? It means the bottom of the slinky doesn't know the top has been released because change in tension travels as a wave that hasn't even reached it yet. In summary, my computational model successfully predicts the motion of the slinky. The physics is clear. As long as the upward tension balances gravity, the bottom stays still. Thank you for watching.